Hello everybody, welcome to the lecture 4 of block 1 mathematics for CFD. This lecture is about pressure field visualization using ideal gas law and Python programming. This class is presented by Dr Aishvarya Kumar. I am a PhD in mechanical engineering from City St George's, University of London, and I work for Skyguru. So let us look at the ideal gas law first. So this is the ideal gas law in the thermodynamic form, or we can say a system form. Here the multiplication of pressure and volume is equal to the multiplication of mass times temperature times gas constant. So here the key idea is that the equation applies to the finite volume of a gas, or we can say a system. Like for example, we can say there is a gas contained inside a box, or we can say gas in a container, and all the properties are same in that container, so we can apply this form of equation. So hence this form of equation takes average values over the entire volume. So let us look at the local form of ideal gas law. What we are doing here is we are dividing the finite volume into infinite number of volumes, and pressure, temperature and density varies locally. Hence we obtain this equation P equal to rho RT, where P is the pressure, rho is the density, T is the temperature, R is a gas constant, and pressure varies in each point in the space. Hence it is written P, and in bracket XYZ same applies to rho and T. So to model the pressure field using ideal gas law in Python programming, we will also need a temperature field. And if you remember the last lecture, we used the Gaussian temperature distribution using this model, where we put the temperature source at the center of the square, which is at 0.5 x and y. So we have this equation T x y equal to 300 plus 50 times exponential of negative of my x minus 0.5 square plus y minus 0.5 square by 0.02. Here 300K is the base temperature, 50K is the strength of the hot region, or we can say the temperature of the heat source, and x is equal to 0.5 and y equal to 0.5 is the center of the hot spot, or the location of the heat source, and exponential term represents how temperature decreases as we move away from the center. So those who remember our last lecture, I wrote a program to visualize the temperature field using the Gaussian model. So if I run the program, I can show you that it successfully visualizes the temperature field. Here the temperature source lies at the middle of the flow domain, and as we move away from the center, the temperature decreases. This is something we expected from this equation, the Gaussian equation, which is modeled in this line here. So now what I will do is I will modify this program and add ideal gas laws here, so that we can use the same temperature field to model the pressure field. So let us start modifying the program. So let us put gas properties. This time we are assuming the density to be constant, but maybe in the next part what I will do is I will try to introduce a program with variable density. R equal to 287 joules per kg Kelvin, and let us write the equation for ideal gas law. P equal to rho times R times T. Now what this will do is, now this program will take T from this equation, the one we defined for the temperature field using the Gaussian model. Now what I will do is I'll just make slight changes in the plotting part. So instead of T, I will just make it P, and then I will just change the label here and I just make it pressure and put pressure in pascals, and just change the title and just say pressure field from ideal gas law, and let us hope this program runs. So I will try to save it first and then use terminal to run it, because last time we had issues. So I'll just use terminal this time, and let's hope it runs. And see, we have obtained the pressure field from ideal gas law. So as the temperature is highest at the center of the square, or we can see at the center of the floor domain, since the pressure is directly proportional to the temperature, the pressure is also maximum at the center of the flow domain. And as we move away from the flow domain, the temperature decreases as we obtained for the temperature. So again, I would like to say thank you for watching this tutorial. For any technical assistance in mechanical engineering design and simulation, you can contact us at info@skyguru.in or email us on our alternative email address indiaskyguru@gmail.com. You can also WhatsApp us on +91 983 983 9753, and if you found this lecture useful, please consider liking and subscribing to support the channel. Thank you.